For the rest of the activity, because the circular motion is a very important and canonical classical textbook example, I'm going to follow exactly the same as the activity. Make sure you do the same thing, do the derivation, do the practice, do the exercise yourself after you watch the video. So the first part, we're going to draw a vector representing the position of an object moving on a circle. So here is our xy plane, and the object should be somewhere on the circle. Therefore, we can draw a arrow representing the vector representing the position of this particle. Now, because the x component of this thing, as you can see, is somewhere here, and the length on the x-axis is the x component of this vector, and also the x location of this particle. So the length over here, which is the radius r times the cosine of this angle theta, this will be the x position of this particle. Similarly, if you look at the projection of this vector onto the y-axis, the length over here will be the y position of this particle. Therefore, the y position of this particle will be r times the sine value of this angle theta. So we can write the vector now in terms of the ijk notation. The position, which is a vector, will be the x location in the I component plus the y location in the j component. We already know that the x and y can be expressed in terms of the radius and the angle theta. So the position will just be r cosine theta I plus r sine theta j. Next, we can use the definition of velocity, which is the derivative of position, to get the velocity of this particle. We can just copy what we get here and do a derivative to it. When you have two terms summing together, you can just do derivative to each term independently. So this will be just the first term taking derivative with respect to t, and the second term. The r is just a number, the radius of the circle, so we can pull it out of the derivative. The I and j are also just constant, so we don't need to do any derivative to it. All we need to focus on is how to do derivative on cosine and sine. So we can pull out the constant, which is in common, to make our equation shorter. Now, this angle theta is a function of time because the object is moving on the circle. When the object is moving on the circle, the angle will change with respect of time. So when we do derivative, we can see that this angle is a function of time, and when you do differentiation on a function inside a function, then you need to use the chain rule. We first do derivative with respect to whatever is inside the function, and then multiply the derivative of the thing inside the function and the t over here. So the derivative of cosine is negative sine, and then you multiply this value, which we are now going to denote as omega, which is known as the angular velocity. So now we have our first term, which will be negative sine times omega. Similarly, the derivative of sine will be differentiating sine with respect to theta times theta dt. So it will be cosine times omega. Therefore, we can see our velocity will be r times the first term will be minus sine times omega I. Let me write the omega in front of the sine because it looks prettier, in my opinion. And then omega cosine j. You can further multiply the r into the parentheses. So it's minus r omega sine for the I component and plus r omega cosine for the j component. Good. So now we have the explicit expression for the velocity of this particle. We can solve for the magnitude and the direction of this vector. We can look at this vector in an easier way. I'm going to pull out the r omega, which is common on both terms, and then write the vector in this form. We can see that the magnitude of this vector, the part in the parentheses, will be square root I component square plus j component square. But this is just sine square plus cosine square and equals to 1. So we see that this thing in a parentheses is a unit vector, so which tells us that the magnitude of this vector will just be the vector in the front. So we can always write a vector in terms of its length times the unit vector representing the direction. Therefore, we see that the magnitude of the velocity is r times omega. And the unit vector pointing at the direction of motion will be this guy. It is always a good idea in physics to try to picture your answer. So let's copy this thing and see what this vector looks like. The sine and cosine can be drew on this circle if we set the radius to 1. So let's say cosine is this length. So this is the length of cosine, and this is the length of sine. Now, the vector representing the direction of velocity has a minus sign for the I component. So I component need to be along the x direction, and it is negative, so it means it's going to point left. Let's draw a vector pointing left with the same length as sine theta. So it's about this long. And let's draw another component, which is the j component, with the length cosine theta. Cosine theta, sine is shorter. Let's use the color blue to represent sine. Cosine theta will be this long, and we can try to add these two components graphically and see that the resulting vector will point toward this direction, and it looks like it is perpendicular to the position. Later we are going to prove that indeed the velocity of a circular motion should be perpendicular to the position of the particle. Mathematically, we can do that. We can check that by computing the dot product between the velocity and the position vector. So the radius or the position vector is somewhere up here. Yep. And the velocity vector is something like we got here, which is this guy. So we are going to dot this vector with this vector. When we compute the dot product, we multiply the I component together In this case, it's going to be r cosine times minus r omega sine. So r cosine times minus r omega sine. And then we can add r sine times r omega cosine. This will give us 2r omega. So it's minus r squared omega with a sine and a cosine. There will be a r squared omega with sine and cosine. So we see these two terms are exactly the same, but 1 plus, 1 minus, which get to 0. Good. So we check that r dot v is 0, which means that the position and the velocity of a circular motion will always be perpendicular to each other.